Okay, this is going to be molecular geometry, the shape of molecules. So let's go ahead and get started. Why the shape of the molecule is important, okay? The shape of the molecule may determine its properties and uses. Properties such as smell, taste, proper targeting of drugs are all possible because of shapes of molecules, okay? I'm going to skip this part. All right, how do we determine the shape of the molecule? You have to draw the Lewis dot structure first. So Lewis dot structures don't give us a three-dimensional, but atoms do bond in a three-dimensional shape, okay? The Lewis dot structure implies that everything's 90 degrees, but in actuality, they are not, okay? So how do we find the shape of a molecule? We use Vsepr, okay? It stands for valence shell electron pair repulsion theory. This is what I need you to write down, okay? Molecules will adopt a shape that is lowest in energy by minimizing. My pen is not working. I don't know why my pen's not working, but copy this part. Let's go back. Copy the main premise. Okay, by minimizing the valence shell electron pair repulsion between adjacent atoms. Okay. So what does that mean? Atoms in a molecule try to spread out from one another as much as possible to reduce the like charge repulsion between the electrons. Electrons don't like each other. They want to be as far away as possible. So let's take methane or CH4. You might think it looks like this right here, but in actuality, it is in three-dimensional. It's a three-dimensional shape. Okay, let's talk about how we get these three-dimensional shapes. There are four main Vsepr types, and we're going to just talk about a few of them. All right, from Lewis to Vsepr shape. We first draw the Lewis structure like we did in class. You count the number of electron domains around the central atom. Each single, double, or triple bond counts as one domain. So these rules right here, you need to write them all down. Okay. Use Vsepr chart to determine the shape based on how many bonding and non-bonding domains are around the central atom. Okay. All right, I have a pointer option here, so that's what I'm going to use. So I don't have a pen actually today, so okay. So regions in a molecule where there are high concentration of electrons. Lewis dot structures show this Lewis dot structure for water shows two domains. It's these lines right here. There's 1 and 2. The two non-bonding domains are these two pairs of electrons that are not bonded to anything. Okay. How many domains around the central atom? There's 4 around this one right here. 1, 2, 3, 4. Carbon is a central atom. This fluorine is not a central atom. Okay. And here, how many are there here? There's 1, 2, 3. A double bond is considered one domain. And here's a triple bond, and there's one domain. Electron domains are all negatively charged, so they want to spread out from one another as much as possible to get away. They just like to be away from each other. Doing this allows a molecule to be more stable with low energy. So here's the chart that I'm talking about in the other ones. You need to memorize this, okay? So if there's two domains, then you're going to have two bonding domains, no lone pairs. You're going to have a linear shape. It's going to look like a line. 3 domains, trigonal planar. Now there's two types, or there's a couple of types here. 3 bonding pairs, 0 non-bonding domains, like 0 lone pairs, is trigonal planar. 2 domains and 1 non-bonding domain is bent. Okay. 4 domains. Okay. So if there's 4 domains and 0 non-bonding, you're going to have tetrahedral. 3 domains and 1 lone pair, trigonal pyramidal. 2 bonding and 2 that are not bonding and they're lone pairs, they are going to be bent. And that's what's right here is the word bent. It looks just like this one right here. Okay? All right. So let's look at some examples real quick. Okay. We did this one in class, CO2, and you'll see that there are 16 electrons, but these two and these two are all domain. These are domains 1 and 2. So there's 2 domains, no lone pairs on the central atom, and you have a linear shape to it. Okay? Okay, so let's take a look at number 2. BF3. You're going to have 24 valence electron. Boron is an exception to the octet rule because it will only have 6 valence electrons. There's 2, 4, 6. Okay, so we have 3 domains and 0 lone pairs. So the Vsepr, we look at the Vsepr chart and we'll see that it's trigonal planar. Okay, so let's take a look at this next one. By the way, when it's in a bracket and has a charge, it's an ion. So NO2 ion has 18 valence electrons. It has 2 domains, and we're looking only at the central atom. It has 2 domains and 1 lone pair. So 2 domains, 1 lone pair, non-bonding. We have trigonal planar again. Okay. However, this is the electron geometry, but the molecular geometry on this one is bent because these two electrons are going to push down on the 2 domains to get furthest away from each other. CH4 has 8 valence electrons. There are 4 bonding domains, and so 0 non-bonding, and so we're going to have a tetrahedral, which is also molecular geometry is tetrahedral. NH3. You have 3 bonding pairs, 1 non-bonding pair. So you're going to have a tetrahedral. However, the molecular geometry is going to be trigonal pyramidal because it's going to kind of form a pyramid shape to it. Water has 2 bonding, 2 non-bonding. So these 2 bonding pairs, non-bonding pairs up here are going to push down, and we're going to end up with sort of tetrahedral, but it's going to be more, but the molecular geometry is bent. Lone pairs create a larger region of negativity charge than bonding domains, and they push down, and that's what I've been saying in the last few examples. Okay. Lone pairs decrease the expected bond angle. So if you notice, the bond angles are getting smaller. Okay. So the number of lone pairs around the atom, if it's 0, 1, or 2, 1 or 2, and there's your approximate bond angles. Okay, so this AXE, the A stands for, and write this down, I can't write it on I don't know why my pen is not working on this one, but the A stands for central atom. So make sure you write that down. The X is the number of bond domains, and the E is lone pairs, non-bonding pairs of electrons. Okay, so if you see this, the subscript tells us how many atoms are bonded to the central atom, and A being the central atom. The E is the subscript, tells us how many lone pairs are on the central atom. And AX3E1 is always trigonal pyramidal, and AX2E2 is always bent. AX4 is always going to be tetrahedral. So There's another way you could see it, and you have lines, kind of a pie shape, and then the little dashes. Each part represents it, and you can just look at this just to know. The bonds are on the plane. The bonds in the plane are in the paper are shown in lines. Bonds projecting in front of the plane of the paper is a triangle, and then the ones going stacked lines behind it are the ones that are showing projection behind the paper. Okay, so make sure that you bring this to class, and I will see you in class, guys.